Hi class. In this video, I'm going to be doing just a tiny bit of review and then going through section 1.1, which is really addressing the fundamental issue of what is a differential equation as we begin our course on differential equation. So the first thing I'm going to talk about is a function. So a function, and I pulled this definition from Wolfram Alpha, is a relation that uniquely associates members of one set with members of another set. That first set is usually called the domain. And as an example, this might be some Rn, just the real numbers, or higher dimensional real numbers. And then the other set that we get mapped to is called the codomain. And an example would be just the real numbers. So you might start off with some x, y, and z, some vector of numbers, and this maps over to some number k. So usually when we think of functions, we think of it in terms of like the actual description of how you do that mapping. So if the mapping is called f, if your function is f, then you'd write something like, f of xyz equals k. And it might be given by a description that looks like, f of xy z maybe equals x squared plus y squared plus z squared. So you have a formula for it. But that's not actually strictly required. Really, a function is just the pairings, just kind of the bag of all the pairings between x, y, that was a bad comma, x, y, z, and k. Like all of those, all of the mappings between everything in the domain, all those triples, and what they're connected to in your codomain. That sort of bag of connections is a function. All right, so the next concept we're going to talk about are derivatives. So a derivative is a rate of change of a function f. If f maps from A to B, then you can sometimes define the rate of change of that function with respect to one of the variables. So the derivative itself is another function. So it is a function itself whose domain is a subset of the domain of the original function. So you may know from other math that you've studied that some functions are not differentiable, that their derivative doesn't exist. And so really that is included in this definition here. For some of the points, some of the values in the domain of the function f, in your domain A, at some of those places, you might be able to take a derivative, and some of them you might not. And if you can't take it anywhere, well, then your derivative just sort of doesn't mean anything. But in some places you will be able to take it, and that's when the sort of normal concept of derivative makes sense. So then another important point here is that since the derivative is a function, that derivative has its own derivative. And so you can take the derivative of a derivative as many times as you like. So we can take derivatives as many times as we like. However, that domain of where the derivative exists may get smaller and smaller and may ultimately become nothing. Okay, so now let's talk about notation. So if f is a function of one variable, which is sort of the usual case that we're used to, like from our first semester of calculus. So, for example, if you have f maps from, let's say we'll call that variable x. So f maps from the real numbers to the real numbers. Then we can write the derivatives a number of different ways. Write the derivatives. So one way, that's kind of the more formal way that you would have first seen it probably. So the derivative of x with respect to x, df dx. And then the second derivative, you do a little squared. So that means two derivatives of f, and they're both with respect to x. And so forth. You can take this derivative over and over and over. And if you do it k times, you get k derivatives. So derivative k times of f, and that derivative is with respect to x, all k times. So the simpler notation that you probably prefer from calculus is, instead of writing the d's, you just write f prime of x. And if you do it two times, you can do f double prime of x, and so forth all the way up to k derivatives. Now you usually put the k, if you can't do prime, you don't really want to write more than like 3 primes. So if you're doing like, the 10th derivative, you usually put it in parentheses so that it doesn't look like you're raising it to a power. And then one more notation that you might see in engineering classes or physics classes is f dot of x and f double dot of x, but that really doesn't scale very well, so you probably only see those first two, and we won't really ever use those in this class. Okay, so that's kind of the easy case where we only have one variable for our function, but we are often concerned about if f is a function of multiple variables, say x1, x2, dot, 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 to xn. So another way you could write this is that f maps from Rn, a vector, just like in my first example. And let's say this maps just to the real numbers again. Then derivatives are defined on each variable separately. And are called partial derivatives. So you'll have seen this in, third semester calculus, multivariable calculus, and things get complicated really quickly. Obviously, you kind of get a good handle on a derivative in just the single variable case, and you're like, okay, well, this is easy enough. And now when you have a multivariable case, there isn't just like a concept of derivatives. Now you have to talk about sort of which variables you're talking about and everything like that. So our notation gets similarly complicated too. So here is our notation, and there are a few different ways you can do it. The formal way, now we use, instead of the lowercase d that I was using before, we have to use these partial derivative d's. So we have our fancy d. So this says that we're taking a partial derivative of f, and that partial derivative is with respect to the variable xi, one of the x's. So let me add a note up here. So this is the notation for partial derivatives with respect to the variable xi. Okay, it could be any one of the x1, x2, all the way up to xn. So if you are just taking one partial derivative with respect to xi, it's how you write it. If you're taking two, now it's basically the same thing we wrote up before, so but with the partial. So we're taking the partial derivative twice of the function f, and that partial derivative is with respect to the variable x both times. And so forth, all the way up to, if we're taking this n times, then it's dn f dxi n. Now there's a shorter way that we can do this, kind of like we had the shorter ways before, and that would look like just the partial with respect to xi of the function f. And then if you're doing it twice, dxi squared of f, and so forth, dxi n of f. And then the last piece of notation here, we have f of xi. So it's the function, and you do sub xi, which just in the context, it should be clear that it's a partial derivative, but this doesn't really scale. So we'll say this is for first partials only. Okay, and then our last piece of notation, sorry, notation is a bear. So let's say notation for mixed partials. So that means that some of the derivatives are with respect to one variable and some with respect to another. And so now we really have to use the formal notation, the first one that we did in the green up above. And so we might have let's say d squared. For one derivative, you can only do it with respect to one variable, so you're not going to have mixed. But if you're doing two, then you might have two derivatives of f, and one of them is with respect to xi, and one of them is with respect to xj. And usually it's the rightmost one that comes first. But actually, usually the order doesn't matter. That's getting into a lot of other stuff. Anyway, my point here is to just kind of like show you that this notation exists and acknowledge that it's really confusing, and that whenever it comes up in a problem, you'll just have to sort of figure it out each time, and you'll get more and more used to it as we get through the problems. So anyway, if we're doing higher order ones, let's say we're doing n derivatives of f, and let's say we're only worrying about two variables, although you could add in lots of variables here. You might have, let's see, k of them with respect to xi, and L of them with respect to xj, and you make a note that k plus L equals n. Okay, so of those n derivatives, k of them were with respect to one variable, and L of them were with respect to another. Okay, moving on. Now we're really sort of beginning section 1.1. 1.1, and we're interested in what the heck is a differential equation. So now that I've spent all this time talking about notation and how awful it is, I'm going to confuse things even more and change up our notation again. So the reason for this is that derivatives describe rates. And in physical applications, we're usually concerned with how things change with respect to time. So the classic example of a derivative that you see in physics class is velocity, right? Which is the derivative of position. So the velocity describes how your position changes with respect to time. So that means that we want our variable to be time. So we will consider a function y of t. Fortunately, we are only worrying about the single variable case right now, so we don't have to worry about all the partial derivatives and stuff really until the end of the class, which is nice. So, an ordinary differential equation is an equation. So you know what an equation is, it's got an equal sign. And that equation involves the function y and its derivatives, y prime of t, y double prime of t, etc., up to the nth derivative. So the general form looks like, the general form of an ordinary differential equation looks like, so by convention, you usually write the highest order derivative on the left-hand side, and this equals some function f of t, and then all the lower order derivatives. And n is called the order of the equation. Now I'm going to give this general form a name. I'm going to call it ODE for ordinary differential equation. So this notation looks like a lot of things. So we changed the notation on our function earlier. So before I was saying f of x, and now I'm calling it y of t. And the t I explained because we're usually interested in the time domain. But why did I call it y instead of f? Well, for one thing, here is another f. Here is some other function. And what this equation is saying is that the nth derivative of y equals some combination of all these other variables. And those variables are going to have basically plugged into them our regular time variable and then all of the derivatives of y. And we used y because usually you think of y kind of like you think of x, where it's the solution to something. And so the key thing here is that the solution to our ODE, the solution to this equation, is a function itself. It's a function y of t. That's what we're after. So we're not trying to solve this equation and get the answer, 7. Our equation's going to look like y of t equals blah, 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 blah. So let's do an example. So here is our ordinary differential equation. And already I'm going to mess with you and write it in a different way. So there's sort of the general form of equations, and then there's the other form that you write them in instead. So y double prime of t plus a, some number a, y prime of t plus k y of t equals 0. So to put this into standard form, we could rewrite this as our second derivative of y with respect to t. So we put the highest order derivative on the left-hand side and then sweep everything over to the right. So it will equal negative a dy dt minus ky. So let's see, let's do blue. In the notation of our definition above, our standard form, that function f is a function. F maps its three variables, t, y prime, and y, onto this function negative a y prime minus k y. So a key observation here is that this is a differential equation, so we expect there to be derivatives, but there are not derivatives of the function f. The derivatives are on the function y, and they're taken with respect to the variable t. So that's important to be able to identify. Let's say that t is the independent variable because that's the variable with which we take our derivatives. So it's the independent variable up in our derivatives there. And then y is the dependent variable. And it's also the thing that we're usually trying to solve for. So an interesting observation is that y is both a function and a variable. So that can be a little bit confusing. And then another term that we use here is that a and k, which are appearing right up here, are the coefficients. So in this particular case, they are just numbers. A and k usually just stand for constants. They could be constants in practice. They could be more complicated than constants, and that's going to be a big distinction that we talk about through the next couple of sections. Okay, so just a couple more terminologies. If all the derivatives are taken with respect to, that's what WRT means, with respect to only one variable, then we call it an ordinary differential equation, or ODE. So that's like the one that I defined up above. And if there are partial derivatives in the equation, we call it a partial differential equation, or PDE. Oops, PDE. We will cover PDEs just in the very last section. They have really much more interesting applications because now you can bring sort of spatial information into the context. When you're talking about physical applications, ordinary differential equations are very useful for dealing with the time domain because it's just time by itself. How are things changing with respect to time? But if you also want to talk about how things change with respect to space, then you get more variables and you need partial derivatives. Okay, so one more subdivision. If the function f from our definition of above depends linearly on y n minus 1, yada, 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 then the ODE is a linear equation. And otherwise, it is nonlinear. So we know about, I'm going to scoot to the side here, we know about linear equations from, high school algebra. So a line looks like y equals mx plus b, right? And this is a line or linear equation. And the sort of standard form of this might look like ax plus by plus c equals 0. And then to generalize, if you had higher order, more dimensions, then you could say something like our coefficients a1 x1 plus a2 x2 plus yada 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 an xn equals 0. And so the important thing with a linear equation is that these coefficients, so let's see, constant coefficients equals linear. Okay. And it's going to be the same thing over in our ODEs. So let's head back over here. So our general form of a linear ODE looks like our nth derivative, so we have order n, yn equals a1 times y to the n minus 1 derivative of t plus yada yada yada, and now a n minus 1 of t y prime of t plus am of t y of t plus g of t. Okay, so now here's what is getting really confusing. Our coefficients even this guy over here, coefficients are not constant in the sense that they are numbers. Coefficients are constant with respect to the y's. Okay, so this is what our definition up here said. The function needs to depend literally on the y's, but not necessarily on t. Okay, so we can have all sorts of crazy things going on with t as long as the y's are sort of normal and don't have any powers in them or cosines or anything like that. Okay, so that can be a little confusing. Let's do some examples. Okay, so our first example will be y double prime plus y equals g of t. And this is linear because all of the things sort of in front of our y's don't have other y's in them. In fact, these have constant coefficients. So we don't have crazy things happening with the y's. We don't have y double prime times y. We don't have cosine of y. We don't have e to the y, anything like that. It's linear, and then it's second order because the highest derivative is 2. So next example, y triple prime plus 5y prime minus y equals 0. And this is also linear because we don't have anything crazy going on with the y's. And it's third order because our biggest derivative is 3. And one more example. Y prime equals y cubed. Now we have something a little bit crazy going on. So first notice that this is a cube, not third derivative. So this equation is non-linear. But you can still talk about the order, and it is a first order. So one reason that we really make this distinction is that linear equations end up being way easier to solve. And just like you know exactly how to solve a linear equation in algebra, you just figure out where the line crosses the axes. And so we often will break down ODEs into problems we can solve and problems we're not quite sure how to solve. And so a lot of this class early on is going to be breaking things down into, well, I don't know how to solve this problem, but what if we simplified it? And then what do we know how to solve? All right, so that sort of covers what a differential equation is. But now let's talk very briefly, and then that'll be the end of this video, about why differential equations. So if you have taken any physics before, you have probably seen a pretty famous differential equation, and that would be Newton's second law, F equals ma, right? So another way to write that, so that doesn't look like it has derivatives in it, but another way you can write it is, so F is force, m is mass, and a is acceleration, which is also equal to the derivative of velocity. And then you can also write this as mx double prime, where x is the position. So what this really says is mass times the acceleration of a moving object has to be equal to the total forces acting on it, F. So this is a second order differential equation on the trajectory or position and trajectory x of t, where the particle is at a given time. Some other applications of differential equations are finance. You may have heard of the Black-Scholes equation. Population growth, because the size of your population is changing at a particular rate. Current can be modeled with differential equations. Radioactive decay, kind of similar to the opposite of population growth. And diffusions, which is how the quantity of something will sort of, go away. So pollution is a good example of that. If you have some amount of, pollution in the air and you know that it's going to be dissipating at a particular rate, then you can study how much there will be left at a particular time. Same thing with heat. Or my PhD work was in using diffusion equations to model image processing. So there's like a ton of different applications, and these things come up all the time in physical applications. So that is why you were taking this class. In our next video, we will start looking at some particular types of problems and how we can begin solving them.